Hi students, so this is it, chapter 6, probability. So in this version, I'm going to go faster. I did a test run of this without the camera, so I realized there are parts that I can go a lot faster on, and so probability here is, in statistical procedures for this particular course in this chapter, is the proportion of scores under a distribution. And we're going to use the basic concept of probability to help us understand how we get this and how we can use probability to start looking at the proportions of scores in a distribution. And so that's the foundation of probability in this chapter. In terms of learning outcomes, there are 5 learning outcomes in this chapter, and they will guide us through this concept of probability in statistics. So the first outcome is to describe and explain the definition of probability. The second outcome is to explain the assumptions of random sampling using probability. The third outcome is to use probabilities and to help us find probabilities using the unit normal table. That is the Z table. And you can find this in your course modules if you're taking the course with us in Alexander College or elsewhere. The fourth outcome is to find scores for a given portion using the Z table. It will be the flip side of outcome 3. And for outcome 5, then we apply what we learned in outcomes 3 and 4 with the unit normal table to help us describe and find percentile ranks in a normal distribution. Again, using the Z table. The math tools we need, as the points say, well, because we're working with probabilities, which is proportions, or which are proportions, we need fractions, decimals, and percentages. And you can think back to our frequency distribution where we did proportions and percentages in chapter 2. We are also going to need basic algebra, not only in terms of proportions, but also in how we find the location and the proportions in the unit normal table. And also, well, because these tables are Z-scores or determined by Z-scores, we need our knowledge of Z-scores as well. And so, introducing probability, we are going to use this for inferential statistics as we approach that point. We start with asking about the entire population, but we can only, most of the time, do research with a sample. And so, because we can only use a sample and use samples to make generalizations or make inferences about the population, then we engage in inferential statistics. And the relationship between samples and populations can be described in terms of probability. So, when we ask questions like, hey, is a sample really the same or different from a population, especially if we apply a treatment to the sample, then we're engaging in inferential statistics where we look at whether a sample distribution is far enough away from the mean or the expected value of the population distribution for us to say, yeah, they're really different, or it's close enough that they're the same. And we use probability to do this. The other way of looking at using probability is, well, how are we going to get the sample from the population? And we want, in random sampling, everybody from the population to have an equal chance of being selected, the same probability of being chosen as a sample. So in terms of the definition of probability then, in a number of courses and lectures and texts about this, the simple definition of probability then is the proportion of the specific outcomes or the number of specific outcomes you're looking for divided by the total number of all possible outcomes. So to do this quickly, a coin toss has 2 sides. So if you want the probability of, let's say, the heads, then it's 1/2 or 50%. If you want the probability of rolling one side of the dice, let's say 1, well, a dice has 6 sides, it's a cube, so then it's 1/6. And that's some percentage there. the lottery here, well, in North America, it would be the 649. Let's see if I can do this for the moment. And before I go with the lottery, yeah, 1 over 6 would be 16.6 repeating percent. So you see the probability gets lower as the number of possible outcomes get higher. And so let's say for 649 in North America, well, in Canada it's called 649, where you have 6 balls and, well, actually no, 49 balls, 1 to 49, and then you draw 6 balls from that pile, and then the combination of the balls, if you get them all, you win the big prize, the grand prize. So the probability of getting a 1 for the first ball out of 49, well, would be 1 over 49, which is about 2%, 0.04%. So again, notice that we need the number of outcomes that is specified, and you make that specification depending on what you're looking for, divided by the total number of possible outcomes. Notice if the number of the outcomes specified is the same, and you change the total number of possible outcomes, then the probability changes. Again, the higher total number of possible outcomes, the lower the probability is. In terms of probability notation, it's fairly simple. P for probability, and then you put the brackets, and then it's the event that you want. So, for example, if you're looking for a probability of drawing a red ace in a deck of cards, there are 52 cards in the deck without jokers, and there are 2 red aces, ace of heart and ace of diamonds. So 2 for the specified outcome divided by the total number of outcomes, well, that's 2 over 52, which is 0.03846%, which is about 3.85%. Okay, so that's the probability of drawing a red ace in a deck of 52 cards. So in terms of random sampling, the definition here is we want everyone to have an equal probability of being selected as a sample from the population. So in the slide, we have an example of this where, if 34 students in the class and we want to have a draw for 1 student to get a $10 Starbucks card, could be 100 and students would be happier about that. But what would be a way that every student would get an equal opportunity? You might think drawing from a hat or drawing a particular card, and we can use the red card as an example. And there are kind of 2 ways of doing this, and I'll show you right now. So here is the deck, and this deck here, I can shuffle it and I can draw a card. This time it wasn't a 4. Cool. So let's say this was the first student and the student drew a 4 of clubs, which isn't a red ace. So if the student keeps the card, then the next person that would draw from this, and this deck happens to have jokers, so it's really 54. But still the technique is the same. Here then, it will be 1 less card from the deck, so I draw again. Okay, well, it's a heart this time. And so I can keep drawing. And this will be for a different student each time. Notice still, if the student keeps the card, then there's 1 less card in the deck each time. So the probability is different for each person. And the probability actually increases as more students draw the card and keep the card. So notice here by the 8th person, which I'm going to do now, the probability is even higher because the number of possible outcomes has decreased. So what that means is the first person, person number 1, would have the probability of a red ace, which I'm just going to put RA here, is 1 over, well, in this deck is 54. Right, so person number 2, well, it's no longer 54, but 1 over 53. And the third person here would have, well, actually it's 2, because there are 2 of them. So here is 50, and I wrote the wrong number, 2, and so on. And so you could wait until you get to the last student. So let's say this is the 50. Well, you don't need this last student. If nobody draws it, you just need the 53rd student. And then you would have, well, hey, wait a minute. 2 out of 2. Well, that's 1. So that person's going to draw a red ace no matter what. Notice, though, for each student, the probability is not equal. So what is the way to make it all equal? So instead of letting the students keep the card, the first person would draw the card. Oh, it's a red ace. Cool, look at that. We already won. Let's try again. In a more likely scenario, well, first person draws the card. It isn't a red ace. So that was 1 out of 54. So you would shuffle the deck again. So the next person also gets 2 out of 54. Not 1 out of 54. Again, there are 2 red aces. So what that would look like then is each person, 1, 2, 3, 4, whatever number, still gets the probability of a red ace as 2 out of 54 each time. So every person would have an equal chance of drawing, and you put the card back and shuffle it again. So in your slides, that is the replacement formula. And that's what that slide is about. In order for each individual to have an equal chance of being selected, the number of possible outcomes must be the same for each person. And this applies to random sampling, where everyone has an equal probability of being selected. So in terms of frequency distribution then, probability is the proportion of scores that is displayed in the distribution graph. Again, you can think back to chapter 2 where we looked at proportions of scores. And here we want to remind you, here, and especially true for this chapter, that portions and probabilities are the same here because the total number of outcomes is everybody in the distribution. So portions of that distribution is a probability. And we'll show you what that means in this picture here. Here's a frequency distribution, and you can count the scores. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 scores. And you can draw and write a frequency distribution. I'm going to skip 7 and 8. And I'm going to follow the order here in descending order. Okay. And then you can do the proportion of X here. And then you can do a percentage as well. And you can see that they're the same. So here I got 1, 6, 1, 5, 3, 4s, 2 3s, 1, 2, and 2 1s. So again, if you remember, well, I counted the scores. So n equals 10. And so yeah, I divided by n. So that's 0.1, 0.1. Here is another 1, so that's 0.1. 3 out of 10, that's 0.3. 2 out of 10, well, that's 0.2, or 1 out of 5. Okay, or 1/5. 1 over 10, that's 0.1 again. And 2 over 10, well, again, that's 1 over 5, but 0.2. In terms of percentages, well, just multiply by 100. 0.1 times 100, that's 10%. 10% again for 5. 30% for 4. X equals 4. 20% for X equals 3. 10% for X equals 2. And 10% for... No, 20% for X equals 1. Notice if you add the proportions and the percentages, the proportions would equal 1 and the percentages would equal 100%. And this distribution is useful because it's simple enough and there happens to be 10 scores. So if you ask questions like, oh, well, what's the proportion of scores that scored 3 or lower? Well, it's 50% because there are 5 people that scored 3 or lower, right? And the other half would have scored 4 or higher, in this case 4 to 6. You can ask other questions like, well, how many people scored 3 and 4? Well, you can count that too. 1, 2, 3, 4, 5. 5 people. You can go, well, how many people scored between 2 and 4? Well, it's 6. 1, 2, 3, 4, 5, 6. And so these are the questions that we're going to ask about distributions. And it's the same technique that we use here when we look at the unit normal table. The unit normal table has made the calculations of proportions for distributions of z-scores, or standard normal distributions. So our first learning check then reviews the stuff on probabilities. That is, well, in a deck of cards that contains royalty cards, that is jacks, queens, and kings, if you randomly select a card from the deck, what is the probability of getting a royalty card, a jack, queen, or king? If you chose B, 12 out of 52, or simplify that, you're right. Well, there are 4 kings, 4 queens, and 4 jacks because there are 4 suits. So 4 times 3 is 12. And the number of total possible outcomes in a deck of 52 cards is 52. So 12 out of 52 is correct. Let's try some true-false questions. A. Choosing random individuals who walk by yields a random sample. And B. Probability predicts what kind of population is likely to be obtained. You can pause and figure out the answer on your own for a moment. And if you answered false for the first one, choosing random individuals who walk by yields a random sample, well, that's wrong, because people who walk by don't have an equal probability of being selected, especially if you consider there are other people who aren't walking that day. Random sample requires everyone in the population, whatever that is, to have an equal probability or equal chance of being selected. Chance here is being used as probability. For B, the probability does not predict what kind of population you're going to get. The population is given by virtue of existence. People exist. We have populations that we look at, but we can't examine them all. So the probability then helps us predict what kind of sample we're going to get. And if everyone has an equal probability of being selected, well, that means it's going to be a random sample. So before we look at probabilities and normal distributions, first let's review the normal distribution. There are 3 points to consider. Just like sand in an hourglass, where the sand piles up in the middle and it flows out to the sides in a symmetrical manner, a normal distribution is symmetrical. It has one mode in the middle where most of the scores pile up in the middle, and the frequencies taper off towards the extreme. So just like a bell curve, you're going to get most people scoring the average, and then fewer and fewer people getting more and more extreme scores, either positive or negative. This means using the properties like symmetry in the normal distribution, we can use these things to help us figure out proportions using z-scores that help us identify those sections, just like we identified sections in slide 11 with a simpler frequency distribution of 10 scores. So now we're going to do it with normal distributions. And so this is a picture of a normal distribution. You've seen it before. It has a mu and a standard deviation. This is a normal distribution and not a standard normal distribution because we are working with x values. The y in this slide is a formula for calculating, what is the frequency in a particular point in the x-axis. But we don't need to use the y formula here. And we're going to use the unit normal table, which helps us figure out exactly how much of a distribution is in a particular area in the distribution. So, for example, if you wanted to find out how much of the distribution is in this shaded area, be it 1 standard deviation away, you can using z-scores and the unit normal table that has a standard normal distribution. So it would be like this. Notice in the previous slide, it is once the shaded area is between the mean and 1 standard deviation above the mean. Using a distribution of z-scores and using the unit normal table, which is a group of mathematicians who have calculated the area under the curve in a standard normal distribution, it will tell you that between the mean and one standard deviation above the mean, there are 34.13% of the population, or there is 34.13% of the population that has these scores. And because the distribution is symmetrical, then the proportion of scores between 0 and -1 standard deviations away from the mean would be the same. 34.13%. So between -1 and -2 is the same proportion as this one, between +1 and +2. Another 13.959%. And then this left part here, this extreme, would have the same proportion, 2.28%. And when you add up all these together, it would equal or approach 100%. And so those are the properties of the normal distribution that we're going to use to help us find proportions of the distribution using z-scores. And we can only use z-scores because that's the standard normal distribution where we can look at distributions consistently using a consistent set of scores. And those are z-scores. So again, to review, the normal distribution is symmetrical. This is really going to help us when we look at the unit normal table. So the section on the left side of a normal distribution would have the same area on the corresponding right side, same area. And also, the z distribution is a standard normal distribution. It's normally distributed, but the scores are z-scores. So that's why we can use this for z-scores, because it applies to any normal distribution, regardless of what it is, because we're measuring z-scores by standard deviations. So here's an example. You can have a distribution of SAT scores, and SAT scores are standardized scores, so it is a standardized distribution. However, we can look for proportions using z-scores. So we transform these SAT scores back to z-scores and then use that to help us figure out, for example, well, what percentage of the population scored above 700 if the mean was 500 in an SAT test and the standard deviation is 100 points. Well, an X value of 700 would have 2 standard deviations away. So what we're looking for then is a proportion of scores where in a standard normal distribution, it is above a z-score of 2. And we're going to do this using the unit normal table. And here are some clues for us. So when we look at the unit normal table, which I'll show you in a minute, the unit normal table again tells us what proportions we're looking for. And without the unit normal table, we only know a few things. So far, and these are values from the unit normal table, by the way. So if you're looking at scores between plus or minus 1, well, in z-scores, well, that's 2 times 34.13%, which is 68.26%. And for plus 2, which is kind of what we're getting at now, between plus and minus 2, well, then that's the first bit, the 68.26%, plus 2 times 13.59%, which would total 95.44%. But notice here, though, we still haven't found the portion for scores, at the low extreme end. The previous slide only wants to know what's the proportion of the distribution scoring higher than 700 on an SAT test, which is higher than 2 standard deviations away. Well, we can do this based on the information we have below, and actually you can tell right there, because this tells us, well, it's 2.28%. So using the unit normal table, though, we can find the same value using more consistent techniques than just this table or this distribution. So here is what a unit normal table looks like. And you can find this in our Canvas modules. If you're taking this class at Alexander College, you can go to our Z table and unit normal table. The Z table gives you the table in a website format, and then it tells you how to use the table as well as the history for it. It even has sample questions for practice if you want to use it, which is right here. And this is the sheet you probably want in a real classroom. We would print these out and everyone gets one copy. In the online classroom, well, you can download this for your own use, and you definitely want to download this one. So, this is the condensed version of this unit normal table, which has Z scores from 0 to positive 4 in this case. 4 being on the very extreme end on the positive side of the standard normal distribution. That means 4 standard deviations away. So notice here, though, there are 3 columns. And this slide helps you look at the unit normal table and figure out the proportions in relation to Z scores. And vice versa, you can look at Z scores in relation to proportions. Column A tells us the Z score, and these are positive Z values. You don't need negative ones because the unit normal table has a standard normal distribution, which is symmetrical. The left side has the same portion as the right if we divide it right in the middle. The proportion of the body from left to right, the body is the larger portion. And so because it's a larger portion and it's larger than 50%, the smallest value when Z is at 0 is going to be 50% and no smaller for column B. Notice the values go up from here. And this would be half. And so B gets bigger as Z gets larger. In the tail column, which is C, the proportion gets smaller as Z gets larger because the line moves to the right. B is covered here, but in this column we're interested in C, the shaded area. So the largest proportion is 50% because Z score would be at 0, and then it'll just move to the right at that point. So notice here, C is 0, but the proportion is smaller as Z gets larger. And finally, column D is useful when we want plus or minus using the property of the symmetrical normal distribution, because a normal distribution is symmetrical. So it is a proportion between mean and Z. So D here is also never going to be larger than 50% because it starts at 0, and as Z gets larger, it approaches 50%, but no larger. So notice here, as Z gets higher, the proportion gets larger, but it never goes above 50%. It only approaches that, with the largest being 0.49997. So you'll see the same properties then in the unit normal table. Here they have an extra picture to help you. If you encounter negative Z values, then think of it as a mirror image of this picture that you've seen already. Again, the body, column B, is the larger portion, and the tail is the smaller portion. You would look at the negative Z value as a positive, locate the proportion, be it body or tail, and then report that. But when you do the calculation, you probably want to draw where it is. So if it was a negative something, negative 1, and then you just want to find the portion below that, well, you would label that and say, I want this area, and this is the tail. I would look at column C, find Z equals 1.0, and then go, okay, this is the proportion, because this at Z equals negative 1 is the same as asking, well, what is the proportion of scores above plus 1? It's still C. So Again, that's one way to use the property of the symmetry in a normal distribution. Again, the instructions here also tell us what the columns mean as well. So here's a practice question for us to try. So for example, if you want to find the value of the proportion of scorers below plus 0.25 in Z, well, the body in the unit normal table would tell you, oh yeah, below this point would be 0.5987 of the population that would score equal to or less than plus 0.25 standard deviations away from the mean. And the tail would have 1 minus that. Notice the body and the tail added together, columns B and C, always equals to 1. Whether you do this mirror image or not, it's the same, when you add the body and tail. And notice here, if you flip the Z score into a negative, the body is still the larger value here as 59.87%, whereas the tail is still 40.13%. So for example, if we look for the value here in our unit normal table, we find 0.25. Well, the values read as 0.5987 and 0.4013. That's what we want. If we happen to want to find the value of plus or minus Z equals 0.25, we can, and we use column D and Z times 2. Just like we can find the proportion of scores, between plus and minus 1 in Z by multiplying in the unit normal table 0.3413. Multiply that by 2, you get 0.6826. And so that's how the unit normal table works. And we can try some more with some practice questions. Right after this slide. Yeah, right after this slide. So again, to review, the unit normal table lists the relationships of Z locations and proportions in the normal distribution. So if you know the Z score, you can look up a corresponding proportion in the unit normal table. Conversely, or likewise, if you know the proportion, you can find the specific Z score location if you're given some values to work with, be it the mean or standard deviation. But once you know the Z score, you should be able to find the proportion once they tell you, if it's above or below or whatever, then they'll let you know. And you can find the Z score. So again, here, remember that probability is the same as proportion because the entire population is a probability of 100% because that's everybody, all possible outcomes. So here are some practice questions for us to try. A is, what is the probability or proportion of the population that has a score that is higher than 1 standard deviation above the mean? For B, it would be, what is the proportion of the population that has a score equal to or below 1.5 standard deviations above the mean? And C would be, well, what is the proportion of the population or the probability of somebody scoring equal to or below 0.5, half a standard deviation below the mean, negative 0.5. And so we can use the unit normal table to help us find these things. Starting with distribution A, well, we know the Z score is plus 1. And so the probability of a Z score being greater than or equal to 1.00, well, we look at the distribution in the unit normal table and locate 1, which we have. And then we need to identify whether it's the body or tail. Well, this is the smaller portion we're looking at, so it's the tail. And so we look at column C. And column C tells us, well, it's 0.1587. So the answer is 0.1587, which is 15.87%. So that's one of the easier questions, solved relatively quickly using the unit normal table in column C. So for distribution B, we're asking what is the probability of somebody scoring less than or equal to 1.5. Well, we can locate first 1.5, which is right here. You can see it at the top row there. Again, we need to identify whether it's the body or the tail. The shaded area tells us that this is the body part, the body of the distribution. And so we use column B. So column B says 0.9332. So we write that down, 332, and that is 93.32%. Done. Okay, for distribution C, we want to find the probability of a z-score being equal to or less than negative 0.05. Okay, now we want to remember a couple things. One is that the normal distribution is symmetrical, so the value we're looking for isn't negative 0.05 or 0.5 because that doesn't exist, but we can find negative point or positive 0.05 or 0.5, I should say. So we locate the 0.5 value, which is right here in the top row this time on the second page. And this time we need to identify what the part we're looking for. In this case, it is the tail, the smaller portion. So again, we don't look at the body even though it's to the left, but again, for negative values, we still need to identify first whether it's the body or the tail. So think this is the tail, it's smaller, and so we need to look at column C. Again, you can use this same process that we're demonstrating right now when you do your practice questions so you don't get confused. Drawing out the distribution is useful, and identifying the part is also useful for us to get the right portion every time. So tail is 0.3085. So 0.3085, and that is 30.85%. So those are some ways we can answer some basic questions about probability using the unit normal table when we ask questions like what is the proportion of the population scoring some range of values. Usually it's like above or below some z-score. That would be the basic form. So here are more practice. Here are some questions that you can ask. Well, this time we're doing two things. One, we are trying to find z-scores instead of proportions, and two, we are using some other columns to help us find the z-scores. So the first thing we want to do is remember the properties of the normal distribution. That is, well, it's symmetrical, that's one, and two, the relationship between z-scores and probabilities. So here, for our first one, the distribution here, well, we know the probability of, for example, some z-score. Here is 90%. This is the body. And this is the tail. And so we want to find either percentage here. You can choose whether it's the body at 90% or 0.9, or whether it's the tail at 0.1. So instead of looking at the z-score first this time, we want to find the proportion. So let's say we choose the body, and we want to find a proportion that is 90% or close to it. Okay. So here, it gives us a chance to show you something as well. You see, if we want to find a z location that is exactly has a body proportion of 90% in the distribution and a tail proportion of 10% in the distribution. And the table here gives us only, okay, Z at 1.29 gives us 0.9015, and then here is, Z at 1.28 gives us 0.98997. That's really close. Well, this time we look for the closest value, and if they happen to be really close to each other and you can average it out, you can. But in this case, it's just the same as, calculating a median for an even number of scores. You average the pair. In this case, though, the closest value, without going over, is 0.8997. And then you notice the corresponding tail column gives us 0.1103. So approximately, the Z value here is going to be approximately 1.28. 1.28. So that's the approximate value. So it is close. It is closer to the mean. So it takes less than 90% of the proportion here and more than 10% of the portion here by about 0.03%. But that's the closest we can find in this unit normal table. So sometimes in your practice questions or your tests, you may be finding yourself in a situation where you find approximations instead of actual numbers, where the table doesn't provide you the exact numbers. So in this one, though, here's one. Well, in distribution B, you're asked, well, what are the Z scores, plus and minus? That would give us a proportion of 60% of the population. So here, the probability then is Z is an equal to something. Oops, that's not plus X, that's negative X. Whatever it is. Some value that's negative and some value here that's positive. Okay, so we need to find out what that is, and so we apply the property that this normal distribution is symmetrical. So half of this is 30%. So we locate 30% in column here, in this case, because it starts from the mean and goes to the Z, we need to look for portion D, or column D. Body has column B, tail has column C, and the portion between mean and Z, that's column D. So we find 0.3 in our column D. So we look for it here. Okay, that's too small in the first page, and we find it. Okay. Again, the closest value here is not 0.85, but 0.84. That's as close as we can get. And notice it is slightly smaller than 0.3. So the Z value then is approximately positive 0.84, 0.84, and negative 0.84. And here then, notice these are Z scores now, not proportions. So then we say the probability of a Z score being between plus and minus 0.84 would be really close, but less than, oops, that's greater than. Really close, but less than, nope, not 30%, but 60%. Because we're only looking at half of it. Because it is between 0 and 0.84. So that's some more practice right there. So let us finish our first half of this chapter with some learning checks before we take a break and go into our second half of this. Okay, so when we want to find the proportion of the normal curve that corresponds to Z being above 0.1 or 1.5, What is the proportion of that? Again, you can think about this logically. Where is Z at 1.5? And the question being asked here is greater than 1.5, so think whether that is going to be the body and the tail. And if you know it's the body, it's going to be probably 50% or larger. If it's the tail, it's going to be 50% or smaller. So again, a couple clues. The standard deviation is pretty large, more than 1. And you're looking for something that is greater than 1, or the proportion of it is going to be greater, or I should say the Z is going to be 1.5 or larger, so the proportion is going to be smaller. So in our unit normal table then, if we go 1.5 and we look at the tail because it's something larger, yeah, it would be this value right here. Very, very small. 0.0668. Okay. True, false here. If each of the following statements, see if they're true or false. For a negative Z score, the tail would be on the right-hand side. True or false? And if you know the probability, you can find the corresponding Z score. Take a moment and think about the first one and see what happens to a negative Z score, where the tail would be. And think about what you would get if you know the probability. For a negative Z score, the tail is on the left side. Just like this table would tell us. This picture shows it very quickly. A negative Z score, the tail is still the smaller portion. It's on the left this time. And the body is going to be the larger portion. That's going to be on the right side, which is the flip or mirror image of a positive Z score. Okay. And if you know, and for B, if you know the proportion, then you can find the Z score in the leftmost column. In this case, it will be column A, which we've just done in the practice question.